A given volume of soil in nature is made up of solid particles and the void spaces between them. These voids can be filled with air, water, or a combination of both. That's why we describe soil as a three-phase system: solids, water, and air. If there's no water in the voids, it's dry soil. If the voids are completely filled with water, it's saturated soil. And if the voids are partly filled, we call it moist soil. To understand how these phases interact, engineers use the weight-volume relationship. To develop this relationship, we separate the soil into its three components: solids, water, and air, just like in the diagram on this slide. From there, we define a few important volume relationships that describe the soil structure, such as void ratio, porosity, degree of saturation. The void ratio, usually written as E, is the ratio of the volume of voids to the volume of solids. It tells us how much empty space exists inside the soil compared to the solid particles themselves. Here's a question for you. Geotechnical engineers often refer to the unit weight of soil as dry, moist, or saturated. Which one would you choose? Leave your answer in the comments below. Check out our next video on relative density, where I'll show why these parameters are so important and what you should take away from phase relationships. If you're an engineer or an engineering student, you've probably seen this figure many times, and maybe even been tested on it. But why is the relationship among unit weight, porosity, and moisture so important? You've likely come across all these formulas, and maybe you were even allowed to use them during exams, yet still found it difficult to solve problems involving phase relationships. In this video, I'm going to show you one of the most important takeaways when dealing with granular soils. Something every engineer should understand: the concept of relative density. Relative density is one of the key values that provides meaningful insight into how well a granular soil has been compacted in the field. Let's say a general contractor reports achieving 65% relative density for a granular soil. How do you know if that's acceptable? First, you need to understand how relative density is calculated. If you look at the relative density formula, this formula shows how dense a granular soil is compared to its loosest and densest possible states. Let's break it down. The maximum void ratio represents the loosest condition of the soil, when it has the largest amount of space between the grains. The minimum void ratio represents the densest condition, when those spaces between particles are as small as possible. The current void ratio represents the condition of the soil you're testing right now in the field or lab. So the top part of the equation, E max minus E, tells you how much the soil has been compacted compared to its loosest state. The bottom part, E max minus E min, shows the entire possible range of compaction. When you divide those two and multiply by 100, you get the relative density as a percentage, showing where your soil stands between loose and dense. If that percentage is high, the soil is well compacted and stable. If it's low, the soil is loose and may need more compaction. Now let's take an example. Suppose a contractor reports achieving a 78% relative density with a moisture content of 9%. Based on the geotechnical report, you find that the soil has a maximum void ratio of 0.75, a minimum void ratio of 0.46, and a specific gravity, G's, of 2.68. Using these parameters, you calculate that the unit weight of the soil is about 18.3 kilonewtons per cubic meter. So, is that acceptable? But here's another question. What if instead of a granular soil, you're working with a cohesive soil, like a clay? Would the same approach still apply? Think about it. The concepts are similar, but the behavior of cohesive soils is very different. Let me know your thoughts in the comments below.